So now we're going to go ahead and take a moment to dissect and investigate this molecule heme. So here is heme on the left-hand side. It is this molecule right here. And in the center of heme are 1, 2, 3, 4 nitrogens. Those nitrogens are coming from a total of 1, 2, 3, 4 5-membered rings. These 5-membered rings are known as porphyrin. Or sorry, the entire structure is known as a porphyrin ring, which is indicated up here. So this is our porphyrin ring structure with 4 smaller rings that in the center of it is an Fe2 plus cation. Now that Fe2 plus can be oxidized to Fe3 plus, which whenever that happens, well then this is not going to work as it's kind of designed or intended to. Now, when we look at the structure, what I think is really important to kind of understand and dissect is, yes, we have these 4 rings that are coordinating this iron ion, and this Fe3 plus is going to be problematic, but what we have also are right here, and then what's not depicted in this figure but is in this figure right here is another amino acid. So one of the things that's very important to understand and recognize about this is that we have this heme ring. In the center of it is an Fe2 plus cation. That Fe2 plus is the mechanism or is the player that helps coordinate and position an O2 atom or an O2 molecule. Now, what this means is that if you were to just have, and I'm going to go ahead and kind of blur some things out, if you, there we go, yep, that's what I want. If you just had a heme molecule with iron 2 plus, well then that iron 2 plus and heme could effectively bind to O2. Okay. Now, whenever that happens, this heme, so isolated heme, so purified heme plus Fe2 plus binds O2 more strongly or stronger than heme plus hemoglobin or myoglobin for that matter plus Fe2 plus. And that's worth noting because another thing that this can bind in place of O2 is this molecule right here, carbon monoxide. Now, let me rewrite that and show you the structure of carbon monoxide. Carbon monoxide has lone pairs of electrons. There we go. There's a molecule of carbon monoxide right there. Now, carbon monoxide can displace that O2. And this heme, or this purified heme Fe2 plus, can bind carbon monoxide more strongly as well. Now, the significance of that from like a physiological standpoint is if you have any sort of natural gas utilities in your home or appliances, whether it's a gas range oven or something like that, then you're going to need a carbon monoxide detector. And that is because that carbon monoxide will very easily displace this O2. And carbon monoxide binding to heme instead of O2 binding to heme is ultimately going to be fatal. Now, what I want to focus on, or what I want to bring back up, is that although carbon monoxide has a greater affinity than O2 does, um, O2 can still bind. Now, what in this model is shown is at the bottom we have a histidine residue. So this is our His 93. Then above, right about here or so, is this His 64. So we've got another histidine ring right here. Those two histidines, what they are doing is they're helping to keep all of this, and it's kind of weird, you're seeing at a little bit of an angle, but help keeping this as a flat plane, as opposed to something like this being the iron in the center. These two histidine residues, histidine 64 and histidine 93, and their protonation state is essential for that O2 being in the right place. Now, with all that in mind, it's important to think about and be aware of the amino acids that are responsible for coordinating this. So your takeaway from this is that Fe2 plus is held at the center of the heme ring. Histidine residues on the top and the bottom of that heme ring help coordinate that O2 and keep it in the right position. Now, CO or carbon monoxide has a greater affinity or is more tightly bound to heme, whether it's heme bound to the protein or free heme, than O2, which is just the reason why carbon monoxide is so toxic. Now, what I was saying about these things being in the same plane, here what we have is deoxyhemoglobin. And in this deoxyhemoglobin, imagine that these are the rings, or these are the atoms of that ring that are, well, ideally held in a flat plane. But here what you can see is that the atoms I'm going to highlight here, here, and here, they're not in a flat plane. Whereas in our oxyhemoglobin, they basically are in a flat plane. Now, the difference between those is this oxygen. Effectively, what this oxygen is doing is it's pulling. It's almost like it puts a little hook into this iron, and whenever oxygen's present, it kind of pulls it up. So it puts all of these atoms basically in the same plane. Now, the cool thing about this is that O2 binding to Fe2 plus causes Fe, or this iron, to kind of go up or raise up 0.4 angstroms. Okay. Now, if you think about the magnitude of that, well, this is on the molecular level. That's a very, very small distance. It's not even the length of a hydrogen bond or any covalent bond or anything like that. The movement is very, very small. So what I want you to take away from this is that when oxygen binds to hemoglobin, it causes iron to move 0.4 angstroms. And that's about it.